Hello everyone, welcome back to a course on memory device technology for AI/ML computing. Let us try to recall what we were discussing in the previous class. We saw that by making some modifications to the gate stack of an ordinary normal logic transistor, you can transform it into a memory device. That was facilitated by adding or engineering something called the charge storage layer. We also saw that depending on what is the nature of charge storage layer, you can classify the flash cell or the flash transistor into two parts, the floating gate and the charge trap cell. And the entire operation mechanism depends on whether you have pulled in electrons from the channel into the charge storage layer, or you have pushed them back into the channel. So if there are electrons in the charge storage layer, we know that it is called the program state, and the program state is unique because in the program state, the threshold voltage of the transistor is greater than the reference read voltage on the gate axis, and therefore the program state is also called to be state 0. This is a point that I missed last time. It is called state 0 because during program state, the transistor is in off state. Similarly, in erase, there are no electrons in the charge storage layer, and therefore the threshold voltage of the transistor is much lower than that in program state. Therefore, the transistor is in on state for the fixed VG read voltage or the reference voltage. As a result, the erase state is also known as state 1 because the transistor is on. Okay. We also saw that it might be easier at this stage to cover the biasing mechanisms for both program and erase operation. However, if we have a clearer understanding of the array level architecture which is used in flash technology, it might be more valuable to see how program and erase is facilitated at the array level. So let us begin our journey by asking the question, how are these flash cells arranged in arrays? Remember, we have been seeing that designing a very good basic memory or storage element is always not good enough. You need to arrange them very intelligently in memory arrays such that the read-write access times are optimized. Not only that, even the bit density is improved. So it consumes very little area and the latency is very low. This is the objective of paying a lot of close attention to array architecture. So as you may have already heard from our second module when we were discussing overall perspective of memory hierarchy, actually flash cells are further subdivided by the way that they are organized in memory arrays. So there are two kinds of organization. One is called the NOR flash and the other is called NAND flash. So let us begin with NOR flash. Before we begin with NOR flash, what we are trying to look at is what is the fundamental unit of a flash array architecture. And as we will see, the fundamental unit is that of a string. A string is defined as a bunch of flash cells connected with each other having one common bit line. Okay, so with this information, let's go ahead and see the NOR flash cell. So what is the NOR flash cell? It is the nomenclature, I would say, is derived or inspired from the CMOS NOR gate. In the CMOS NOR gate, as I have indicated by these red dotted lines, the pull down transistor or the NMOS transistors are connected in parallel with each other. You see, they have a common, the drains and the sources are connected to each other and therefore they are in parallel configuration. Exactly the same thing happens when you look at the string of a NOR flash cell. What is a string? As I described, a string is a entity or a bunch of flash cells which are connected by the same bit line. You see, the bit line is the same throughout this string of NOR flash cells. So why do you say that NOR flash is connected in parallel? This is because if you notice clearly, all the flash cells, the drain are connected by the bit line. So this is the cell of the drain of the first cell connected to the bit line, second cell, third cell, so on and so forth. Whereas the source of every cell is connected to the source line, right? So source is connected to the source line. The source of the second is connected to the source of the second transistor connected to the source line, source of the third transistor, and so on and so forth. Okay, so this is what facilitates the parallel configuration in NOR flash cell. Why? Because the bit line is connected to the drain of each of the cells in the string, whereas the source line is connected to the source of each of the strings. So what is the word line connected to? The word line, as we have discussed, is connected to the control gate of every string. So every unique every unique cell in the string has a unique word line, and they are connected to, and the control gate of every cell is connected to a unique word line. Okay, so this kind of encapsulates what is the configuration of a NOR flash cell. Before we move on to the NAND flash cell, I would like to highlight that you see a slightly different schematic that is used for a memory cell or a storage flash cell. Generally, transistors are indicated by this symbol, the same symbol as a flash cell, with the exception that instead of having two vertical lines to represent the gate stack, you generally have only one vertical line. So these two vertical lines are indicated that the normal transistor's gate stack has been modified and converted into a flash cell or a memory cell. So this is a schematic that we should all be familiar with. With this, let's move on to the NAND flash cell. And as you may understand, the NAND flash cell's nomenclature is coming from the pull down region of the NAND gate. So the pull down region of the NAND gate is serial in nature. As you see, these two pull down transistors A and B are connected serially, and this is exactly what happens in the NAND flash cell as well. Only one end of the bit line is connected to the drain of the first transistor in the string of NAND flash, whereas the source line is connected to the source of the last transistor in the entire string. So how are they interconnected with each other? As you can see from this diagram, the source of the first transistor is connected to the drain of the next transistor, and so on and so forth. So to summarize, the source and drain of the transistors are interconnected with neighboring cells, and only the first transistor in the string is connected, the drain of the first transistor in the string is connected to the bit line, and the source of the last transistor in the string is connected to the source line. And that is why we call it to be a serial connection. Just like in a NOR flash cell, however, the word lines for each of the cells which are fed into the control gate are unique. Now, important to note over here is, again, to see that the beginning of the string and the end of the string actually does not consist of a flash cell. How do we say that? The beginning of the string and the end of the string, if you look very carefully at the transistor schematic, it does not have the two lines at the gate stack, which you notice for the memory cells. So these are essentially not memory cells, but normal transistors. They are called the source select line and gate select line. They are normal logic switches, normal logic transistors, and they will play a very important role when we look at the read, write, erase operations, program operations of the NAND flash cell. Okay, with this, we understand that the NOR flash cell has a more parallel architecture, whereas the NAND flash cell has a more sequential or serial architecture, where the cells are connected with each other. The source of one is connected to the drain of the other. Okay. So a natural question will come to our minds is, why is this NOR and NAND architecture implemented? And this could only be understood by moving a little bit deeper into the two architectures, by leaving out just schematics and start looking at the so-called cell layout. So as you know, we have been looking at cell layouts. The cell layouts are done to facilitate compactness in the design, to have smaller area of the cell in the design. And that is exactly the motivation even in NOR and NAND flash. So if we look at the cell layout, we will see that the previous layout was slightly to be modified to favor more compactness in the design. For example, in the NOR flash cell, to make the design very compact, usually two adjacent floating gates share one source line via a contact via. So as you can see, two neighboring select lines not only share a common source terminal, they are also sharing a common drain terminal. So if you see in the vertical cross section, these two cells, neighboring cells, are sharing the common source terminal, and where all the source terminals in fact are tied to each other, and the two neighboring cells, the other two adjacent cells, are sharing a common drain terminal, which is finally connected to the bit line of the cell. Okay. Why is this done? This is done to make the design much more compact. If you look at the top view of your cell architecture, you will realize that the minimum bit line pitch, so this is the minimum bit line pitch. So the minimum bit line pitch is 2F, where F is the smallest feature size, where 1F is for the wire and 1F is for the isolation. However, the word line pitch, or sometimes it's also called the contact poly pitch, is designed as 5F. Where is this 5F coming from? Half of F for each of the two contact vias, 1F for the spacer and 2F for this particular gate length. Okay, so the width of this cell is 2F and the length of the cell is 5F. Therefore, making the area of this entire cell to be 10F squared. Now remember why I have put a sad smiley face when it comes to 10F squared. This is because even your DRAM offers you 6F squared area scalability. So 10F squared, when it comes to flash, is not really desirable because it is worse off than even DRAM. Okay, but there is one thing that DRAM does not offer, which positions NOR flash for certain niche applications that we will discuss, and that is the ability to have non-volatile access. Remember, DRAM is essentially volatile. Once you switch off power, the data is lost. But in NOR flash cell, the data is non-volatile. What is the price you pay versus DRAM? It is the area. Area increases from 6F squared to 10F squared. Now, with this, let's look at the NAND flash architecture. In NAND flash architecture, remember, two neighboring cells are just connected to each other. The source of one is connected to the drain of the other. As you see over here, the source of one is connected to the drain. Source of one is connected to the other drain. Whereas the starting of the string is connected to the bit line via the source select transistor, and the end of the string, the source is connected to the ground via the ground select line. So this gives you lot of benefits in area compactness. So if you see the cell architecture of your NAND flash, you will realize because there are no adjacent contact vias, the area layout can be just 4F squared. The bit line pitch is also minimum 2F, 1F for the wire and 1F for the isolation, and the word line is also minimum. because there are no contact vias between the two neighboring cells. Therefore, it is very essential to mention that NAND flash effectively achieves the highest theoretically possible density in a 2D plane, which is of 4f squared. And this is what gives NAND flash a very distinct advantage. But what is the bottleneck, or what is the trade-off? The trade-off is that since it is essentially sequential, connected. All the flash cells in a string are sequentially connected. The access of a NAND flash cell is also sequential. It is not random access at all. Whereas NOR flash, you can have byte and word level random access. In NAND flash, you can only have sequential access. But since the sequential access, which will be much slower, is also non-volatile in nature, it can be really effectively employed for very high density storage. And this is why the trade-off between area and sequential versus random access between NOR flash and NAND flash lends it very important distinction in the use cases, or in the places that they are employed in the entire memory hierarchy. So as we can see, whereas the NOR flash is implemented for storing very tiny amount of code, which is the boot up code, which is immediately required, where you cannot compromise on the latency. The NAND flash is used for having massive main storage. So they are the point we have to emphasize is, although the storage element, which is the flash cell, is identical, just by the virtue that they are arranged in different manners in the array architecture, their behavior completely changes. How does the behavior change? The read latency is very tiny, comparable to DRAM for the NOR flash, which is roughly 80 nanoseconds. Whereas for NAND flash, it is 10 to 100 microseconds. Several orders of magnitude higher, almost 4 to 5 orders of magnitude higher. Whereas the write ability for NOR flash is very slow, but the write ability in NAND flash and the cycling is very good. Because write ability is slow, NOR flashes are generally used to store data, which is absolutely essential during the boot up of the device. That is why boot code, security codes are stored in the NOR flash. This is primarily because from NOR flash you can very quickly access non-volatile data. So that is why boot up is necessary. Boot up code storage in NOR flash is necessary, because when the system shuts down, some part of the code has to be restored. And when the boot up happens, it has to be retrieved very, very quickly. Okay, so very different use cases for NOR flash and NAND flash. And I hope this is a very quick recap when we did the tear down of our MacBook Pro. Remember, this is what we were doing during our module 2. After we had finished studying the memory hierarchy theoretically, we looked at some practical implementations of the memory hierarchy. At that time, I had emphasized that there are two different array architectures for the flash cell. One is your NAND flash and other is your NOR flash. And even at that point, we had highlighted that just look at the difference in the areas of NOR flash and NAND flash. That is very, very remarkable. When you compare the difference in area, you can see that the area of the NOR flash between the and NAND flash is roughly 4 to 5 times. It could not be more than that. However, if you look at the storage capacity, it is quite remarkable. Whereas the NOR flash stores only 8 megabytes of data, the NAND flash is storing 256 gigabytes of data. So that is how much of an impact there is in the bit density between NOR flash and the NAND flash. So almost a 32 times better bit density with only 4 to 5 times more area in NAND flash compared to NOR flash. What did we study in the previous slide? That the minimum dimensions of, or the scalable dimensions of NOR flash is 10f squared, whereas for the NAND flash is 4f squared. But this does not explain. Just 10 times to 4 times is roughly 2.5 times in difference of the area scalability. But in actual chips, we are seeing that this bit density is much larger, several orders of magnitude larger than what is explained by the cell layout. So the final bit density cannot be only explained through the cell layout difference is in 10f squared and 4f squared. So something very interesting is happening, and that is what makes a NAND flash very scalable, and it makes us really look deeper into what happens with NAND flash memory. So as some of you may already remember, it is true that 2D single level cell have a bit density or the smallest scaling cell size of 4f squared, but human beings have not stopped there. What they have tried to figure out is a single, but this is only for a single level cell. As you may remember from our discussion in module 2, there are other elements in the NAND flash that can be scaled, not just the cell area. So we are going to discuss this in detail. I'm just providing a very quick motivation why we have to look at NAND flash very seriously. And that is, the first is bit or logic scaling. In bit or logic scaling, what we do is we realize that there is a potential that not just one bit data, not 1 and 0, not just program and erase states are possible to be stored in a NAND flash cell. There can be multiple bits that can be stored in the same flash cell. What does that give us? That gives us bit density. Immediately, our area becomes from 4f squared to 4f squared by n, where n is the number of bits that you can store. So today in market, you have MLC, which is multi-level cell, which is essentially 2 bits per cell. You have TLC, which is a 3-level cell, which has 3 bits. And you have also QLC, quad level cell, which has 4 bits. Remember, 3 and 4 bits is 2 to the power of 3, 8 states, and 2 to the power of 4, 16 states within the same flash cell. And by cramming in more bits within the same flash cell, you can really improve the bit density of the flash cell. Not only that, there is another form of scaling which is possible, which is called vertical scaling. Remember the example that I had given? 2D NAND is more like building row houses, but vertical scaling, which is 3D NAND, is more like building skyscrapers. So now you are able to scale in the vertical dimension also. This is called 2D to 3D NAND flash, and this gives you further improvements in areal bit density. Why? Because not only are you cramming more bits into the same footprint, but now you're also creating a tower of flash cells which are vertically integrated. These are the two important things which has made NAND flash such a powerful and important technology. And this bit scaling and vertical scaling is something that we will look at very carefully. And this makes NAND flash the primary focus of our study from now on. Since NAND flash is our primary study, focus of study because of these great advances, let us conclude our lecture by looking at the overall NAND flash array architecture. Once we are familiar with what is the NAND flash array architecture, it would be much easier and more valuable to discuss what are the different program, erase, and read operational cycles that are facilitated through very intelligent biasing schemes in the NAND flash array architecture. So let us understand NAND flash array architecture with a very simple example. Examples really help us illustrate our points. So the example that I'm going to take is that of a 2 GB NAND flash array. So how is a 2 gigabyte NAND flash array organized from the top down, from a top down perspective? So first what we see is that a 2 gigabyte NAND flash array will actually be organized in 2048 blocks. This is the first technical term I am introducing now. So the fundamental unit of a NAND flash array, which makes things NAND flash very powerful, is a block. So right now just note down the term. We will go into details of why this block is important. So 2048 blocks. So of course each has to be 1 MB, because 1 MB into 2048 will give you 2048 MB, which is 2 gigabytes of total data. So as you see, they are stacked up into blocks, block 0 to block 2047, each of 1 MB. So this is what constitutes a NAND flash array. So now let's go and see what is happening within a block. Within a block, a particular block, which is 1 MB, is now further subdivided into pages. What is the meaning of page? Also, we will look in very great detail, but let's now just look at the overall top perspective. So in 1 MB block is generally divided into 128 pages. Of course, the number of blocks and their size may vary a little bit, but these are some general prescriptions that are used nowadays. So 1 MB block is divided into 128 pages. You can see that if there are 128 pages in 1 MB, you can just calculate very quickly that each of the page will have 8 KB of data. So this one block, I have now zoomed into one block and I find out that it is constituted of 128 pages, constituting of 8 KB data per page. Now, important to note that every page has 8 KB, which is the minimum that is required, plus some extra number of bits or extra number of storage space, which is also called metadata. This is used for error correcting and additional storage, which we will not get into at this moment, but it suffices to know that 1 MB block is divided into 128 pages of 8 KB information each. Now, we will go in an understanding what is the representation. How do we convert this top level perspective into what we understand, which is individual strings of NAND flash. So this is the array level implementation of the page and the string. So let us look into this array level implementation, which I have marked out in yellow color over here. As you can see that one particular block, so this is a block diagram in terms of individual constituting of individual strings. As we had defined previously in today's class, that a string which is marked here in purple color, you see this is one string, constitutes of a common bit line. So this is the common bit line for this particular string, which has been marked in purple color. Of course, a string consists of interconnected flash cells. The first part of a NAND flash cell, remember, is not actually a memory element but a logic element, which is called the source select line. The last is also not a memory element. It is called the ground select line. Rest everything are flash cells and they are interconnected with each other. The source of one is connected to the drain of the other. So this is what the string is. We had already studied this. Now what is a page? A page is nothing but one individual word line, and this is what has been indicated by this blue marking. You see, one page is nothing but one word line. Since one page is nothing but one word line, for this particular example, since we decided that the number of pages was 128, within this block there will also be 128 word lines, because a page is nothing but a word line. There will be two additional connections going to every block in the form of the source select line and ground select line, in addition to the 128 word lines which are going to every block. In addition to having 128 word lines per page, there will also be several bit lines. So let's see how many bit lines will be there. If you consider a single level cell, the number of bit lines will be equal to store 8 KB of data. Therefore, as we know, 8 kilobytes of data is 64K cells or 64,000 cells. So the number of bit lines will be 64,000 in this particular example. Just to recap, a particular block is the fundamental unit of every NAND flash architecture. A block consists of several pages, which is nothing but synonymous to the word line, and several strings, which is synonymous to the bit line. In this example, there were 128 such word lines or pages and 64 K bit lines. So a natural question that comes to our mind is, why have we organized the NAND flash array in terms of blocks, pages and strings? And that has got to do with the write and read usability. So the block, as we will see very soon, is the smallest erasable unit. And this is where the term flash comes from. Remember, we studied in our introductory class in NAND flash that flash comes from the term camera flash, where things are erased in a quick instant. In one go, large chunks of data are erased. So this block is the fundamental unit, the smallest unit which gets erased at one go. So generally, the size of a block in modern day NAND flash architectures is around 128 KB to 4 MB. So in our example, we took just 1 MB. The second important element is a page. What is the page? The page is the smallest read-write unit possible in a NAND flash cell. And this is not very difficult to understand. This is the case because one particular page constitutes of an entire word line. So when you read and write, or when you program and read out data, you see that it happens at the level of the page. Whereas erase happens in the level of a block, the program and read happens at the level of page. Finally, we also saw the string. The string is nothing but a bunch of flash cells connected by the same bit line. So this concludes our study of the NAND flash array architecture. We will meet in the next class where we will begin to explore how cells are programmed, read and erased in the NAND flash array. Thank you very much. See you in the next class.